Hello everyone, and welcome back to the second video and final video, actually, in this very short unit about sampling distributions. Now, this video in particular is going to deal with the concept that is probably the most important for the rest of our class after this, which is called the central limit theorem. It is what every confidence interval and every hypothesis test rides on in order to be able to perform the test. And so the video before this, you were introduced to sampling distributions and what they are. In this one, we're going to take that one step further and talk about why they're important. So let's jump right into it here. The central limit theorem itself states that essentially, the larger and larger your sample gets, the more close to a normal distribution your sampling distribution appears to be. Now, what's really, really important here is that for means, this number is 30. For proportions, we need to have 10 successes and 10 failures. And so, to demonstrate this idea, I have a little demonstration for you. It's actually the same applet that you saw in the last video. So if we take a look at that, right now, if you remember here, if I just do this, one thing that is important about the central limit theorem is that if your population is normal, your sample size does not matter. Right? But let's say I take this population and I make it skewed left. With a sample size of 5, notice how my sampling distribution is still skewed left. But maybe I make this now 16. That's starting to look better. And then if I make it 25, which is as close as I can get here, this essentially looks approximately normal. No matter what shape I make the population, right? I tend to make this thing I call the city skyline, whatever this thing is, right? If I take a sample of 5, this is going to look like it looks all wacky. I don't really know what it is. Right? It looks even worse if I take a sample of 2. Right? It looks like another city skyline. But if I take this and I make my sample size 25, it's not perfect because, as we said before, the sample size that you actually need is 30. But 25 is pretty close, and all of a sudden I can look at this and it is almost approximately normal. And so having that large sample size is really, really important. And once we meet that, it is paramount to everything we do. So let's talk about why. The reason why the central limit theorem is so important is that we typically don't know the shape of our population. We don't know if it's approximately normal. We don't know if it's skewed left or skewed right or some weird looking shape like you just saw. And so in order to guarantee some element of normality, this is what helps us do everything from here on out. Because we're going to take a sample mean or a sample proportion and look at where does that fall on the sampling distribution. Or with a confidence interval, we're going to take a sample proportion and cast a net in either direction to try and capture the true population proportion or population mean. So everything going forward now is no longer based on one individual, but based on the sampling distribution of a given population. Because I don't know what the population looks like, I have to do the next best thing, which is use the sampling distribution that I know I can make approximately normal if my sample is big enough. Yeah, I mean, that is the crux of everything that we do from here on out is this central limit theorem. So let's take a look at an example question here. Right? This is from 2009, and it's a tire manufacturer, and it's about stopping distance. Right? Now, parts A and B here just deal with, like, part A is a z-score, find the 70th percentile. So you would find the z-score for the 70th percentile, plug it into the z-score formula, get back out a number. I don't know what it is. Part B is actually a binomial question, right? What is the probability that at least 2 out of 5 randomly selected cars, right, trials independent, etc. What I want to focus on is part C, which is what is the probability that a randomly selected sample of 5 cars will have a mean stopping distance. When I see wording like that, a sample of this size will have a mean of this or more, that is the giveaway to me that this is now a sampling distribution question. All of the sampling distribution questions that you will see and central limit theorem questions you will see are z-score questions. So let's jump into this here. The other important thing here that you might be saying is like, wait a minute, didn't you just say that n needed to be greater than or equal to 30? Well, guess what we got in the problem right here? We know the population is normal, so the sample size doesn't matter. So when I look at this, right, of at least 30 feet, I get 130 minus, remember, this 125 is really the mean of my sampling distribution, but it's the same as the population mean. The only adjustment now, instead of the standard deviation being 6.5, it's going to be 6.5 over the square root of 5. And we get whatever this number is. I don't know what it is. It's 5 over, let's call it 5/3 for fun, right? And then we're going to find the probability that our z-score is greater than 1.67, which in this case gives you about 9%. So there's roughly a 9% chance or a 9% probability that this randomly selected sample will have a mean stopping distance greater than 130. Very important wording gives away what you have to do with the question. So I hope that was helpful. I'll see you guys in the next videos that deal with this for the rest of forever.